Hi everyone, welcome to our week 7 live stream. Since it's 12, I'm gonna go ahead and get started. If you have the worksheet with you, please feel free to pull it out and follow along with me. All right, this week we're gonna be looking at behavioral and population ecology, and first we're gonna be focusing on the behavior aspect of it. So the first part of this worksheet is mostly going to be figuring out how we can ask the right type of question in order to figure out the exact information that we're looking for. So here's the premise. Some plant species, for example, many orchids, rely on a single species of insect for pollination. If the insect species dies out, so will the plant. In parts A through C, refer only to the behavior of the insect species. Okay, so the background information that we have now is that certain types of plants rely on only one species for pollination, and it's also known that if that specific species dies, then the plant dies along with them as well. So we're going to be looking at it from the perspective of the insect and trying to figure out how we can get these information. So the first one is, what kind of questions would you need to ask to determine proximate cause of this behavior? So, can anyone tell me what proximate causes are versus ultimate causes? All right, I see a chat. It says genetic causes and ultimate causes uh, would be like evolutionary causes. Yeah, so I kind of see that with the ultimate causes. What you've described reminds me of ultimate causes because we look at that in terms of evolution, like how and why the behavior came to be. And then the proximate cause would be what mechanisms enable that organisms to be able to exhibit that behavior. So the main thing I would remember is ultimate, think of in terms of evolution, and proximate, think of in terms of mechanisms that allow for an animal to behave in a certain way. All right, so the first question, or question A, is asking us about proximate cause. So we need to look at what mechanisms enables the organism to behave that way. And we're looking at it in terms of the insect species. So some questions we can ask are, what are the specific characteristics of the orchid and the insects? This will help us figure out some of the mechanisms. Another one we can have is, um, what about their morphology that only allows the insects to be limited to one flower? So this is kind of asking, why is there only one insect to one plant? And that would also be a proximate cause because it's talking about their mechanisms and their ability to do so. Another questions that you can ask is there specific insect species that are unable to pollinate other flowers? So this is kind of a similar question, but looking at, are they unable to? And then other things you can look at are color pattern, fragrance, type of nectar, everything else that might draw the insect to only this type of orchid. All right, so part B, now we're looking at the ultimate cause, and this is more about evolution. So a question we can ask here is why would this type of symbiotic relationship between orchid and pollinator evolve? So that would be the ultimate cause of why we see this behavior. Or the answer to this question would let us know why this type of behavior exists. All right, and then C is asking what kind of experiments or investigation would you propose to answer at least one of the question in part A and part B. So there's multiple correct answers here, but for an example, I'll do what factors draw the insects to the flower. So in order to test this question, we would need to test each factor separately. That's very important. So we can avoid having the confusion of which variable is actually causing the change. So we need to test each factor separately. How we can do this is we can place individual insects in a test chamber, and then we can test for nectar preference. So we might have like one plant exhibiting one type of nectar, another one with another type of nectar, and then we can see which one the insect actually prefers. So that way we can see, okay, is it the nectar that it prefers? And if so, like what type of nectar that it prefers. Uh, we could also observe their insects like response to the different types of nectar, whether they only go to one plant and how often they go to that nectar. Is it like every 5 minutes, every 1 minute? So that would let you know how much they prefer the nectar. And then we could also do the fragrance. And for fragrance, we would need to get rid of the nectar because we need to test each variable separately. So we would get rid of the nectar component part, and then we would test for fragrance. So have different types of fragrance, see which one the insect prefers. And we can do that with any other factor that we're trying to test here. So that could be one way to investigate the questions that we proposed above. Any questions so far? All right, not seeing any questions. All right, let's move on to question 2. This is going to be similar to the question that we did, but in a different scenario. The scenario is many bird species common in the northern United States during spring and summer fly south in the fall to overwinter and feed in Central or South America. In the spring, they return to the northern United States to breed. So, what questions would you need to ask to determine proximate cause of this behavior? Comment says no questions yet and finally made one of these review sessions. That's awesome. Yeah, I'm glad you're able to make it to this time. All right, let's see. Okay, what questions would we need to determine for proximate cause? So one other question we could ask for the proximate cause is how do birds know when to fly north? Because that's the mechanism that they use. So that would be one of the proximate cause of behavior. Um, have a comment that says, can one be what drives the birds to fly north? Let's see. Yeah, I think, yeah, that would definitely be proximate. But if you were to word that question a little differently, if you said, why do the birds fly north? And like, why do they have that behavior? Then that would be your ultimate cause. So yeah, the drives for why the birds fly north would be proximate. So let me write what drives. And then I'm going to do the ultimate cause, like wording that question a little bit differently, and that would be why do birds fly south or north? And then another one for the ultimate would be why would this type of behavior evolve? All right. So similarly, we're going to do like what kind of experiments we could propose to answer. So say we're looking at environmental factors that promote them to fly south. We could test that by looking at the change in day's length on birds' behavior. So for example, we could like put them in like chambers with like artificial environment and like control the amount of light that they get and see if the amount of light that they got affects whether they fly south or not. But yeah, there could be multiple correct answers for these questions. It just depends on what question you pick. All right, any questions so far? All right, let's look at the next question. This one's a little bit long. It says many species of animals engage in complex courtship rituals. Among these species is the bowerbird of Australia. Male bowerbirds construct elaborate structures or bower from twigs, leaves, mutton moss, and decorate them with colorful objects such as berries and shells. The bowers and the dances the male perform are designed to attract female bowers for mating. After mating, the females fly away to build a nest and raise the offspring. The males remain at their bowers and try to attract additional mates. These birds can live up to 17 years. Males are territorial and build their bowers in the same location each year. In studying this behavior, researchers have noted about 25% of females shop around, going from one bower to another before deciding on a mate. The other 75% appears to go directly to a single bower to mate. These behaviors cannot be observed in captivity. Okay, so they just described certain behavior between male and female bowerbirds, and then at the end, they conclude that by saying that these behaviors that they just told us about are not observed in captivity, so they're only observed in the natural environment. So we're going to be asking some questions to figure out why that might be. So one question we could ask to determine the proximate causation could be to ask what characteristics of the environment triggers the bower building response in male, because the question pointed out that it's only observed in nature, not in captivity. So asking a question like that would help us determine the characteristics of the environment. And then for the female proximate cause, we could ask, what about the male's dances that trigger mating response in female? Because they talked about how 25% go from like one male bird to another bird to like scope out, whereas the 75% just chooses one. So we can look at what about the dance that actually attracts the female. Okay, and then for ultimate causations, we could ask, why did this elaborate mating ritual evolve in the first place? What evolutionary history led to the behavior? So, from the three questions that we've done, you can notice that for proximate causes, we use characteristics a lot, like what characteristics of something led to this behavior. But then for ultimate cause, we always use the word either develop or evolutionary. So, be aware of those keywords that can help you determine between whether it's proximate or ultimate. And also another thing that you can notice is for ultimate, we tend to start with why did something happen, whereas for the proximate, we tend to use what characteristic triggered something else. So what tends to go with proximate and then why tends to go with ultimate usually. So don't use it as like 100% rule, but just like quick things to like focus on if you're like pressed for time. All right, and then similarly for the last question, what kind of experiment we could do to get an answer to some of that question? So So if we're looking at what characteristic of the environment triggers the male burrowers to build, maybe we can study, well, we can't study them in captivity because we know they don't exhibit that behavior. So we would need to study them in their own environment. So maybe we can look at like the days and weeks leading up to the behavior and compare that to like the rest of the year to see if we're able to find a difference. And maybe that difference can give us a clue to what in the environment triggers the male borrowers. Okay, next we're going to be switching our gear to look at population. And before we move on, do you guys have any questions on any of the questions that we've done so far, or how to determine between ultimate versus proximate causes? Okay, I haven't seen any questions so far, but if something comes to you later, feel free to put it in the chat, even if it's from above. All right, so we're going to be looking at how people actually determine population size in the wild. So, to measure population density, well, here they're using chipmunks as a specific example, but this can be done with different organisms. Like, I remember in high school, we did one with bees. Like, you would capture bees and like put a little red dot on them and then release them back again and see if we like captured the same bees. But here they're talking about chipmunks especially, and they want to measure the population density in a specific park. And what they did is they made several quadrants and captured 50 chipmunks, and they put a mark on each of their back with a small dot of red paint, and then they released them back into the nature. And then the next day they captured another 50, and among the 50, they found that only 10 of them were marked. So, using this comparison, like how many they marked versus how many they were able to capture that were marked in the next day, you can use that to estimate how big the population is. So, how many chipmunks might be in that population. And to do that, there's this formula. And here's what they mean. So, the M2 is going to be number of recaptures in second catch divided by total number in second catch. That is equal to, so you're setting up a proportion for a number marked in the first catch divided by the total population. So usually we're trying to find this. So this is usually the unknown. So in this example, the number of recaptured in the second was 10, and then total number in the second capture was 50 because they caught 50 in the second capture, and only 10 of that were marked. So it would be 10 over 50 equal to number marked in the first catch, which was 50 because it says here that they captured 50 chipmunks, and then this is what we don't know. So if we set up the proportion, how it comes out to, it could be 10n equal to 50 times 50, and then you can divide by 10, and then n equals 250 chipmunks. So that's your estimate of how many chipmunks could be in the population. Okay, did that make sense to everyone? All right, so we're gonna be looking at more questions. So later we discover that you've sampled the one area in the park that was most favored by the chipmunks. So what effect would this have on our estimate? So this new thing tells us that the area we picked is preferred by chipmunks way more than like any other area. So how would this affect our discovery? Would our estimate of the population would be larger than it actually is, or would it be smaller? I have a comment that says larger, and that is exactly right. So if we picked a part where chipmunks just love to come, then we're going to end up capturing more than we would have in a different part of the location. So we tend to get that, like a sample tends to be like higher in that specific location. So our population estimate would tend to be larger than if we had sampled more parks, which is why it's usually like a good practice to test more than one location when we're doing this, so we have more samples to compare and we don't have certain biases like this. So this would cause us to overestimate the population. All right, the next one is, I found this one a little funny. So you later discover that the chipmunks were licking the marks off of each other's backs. So how this would affect is that we would capture some chipmunks that were counted as unmarked that could have had their marks licked off. So essentially they're just getting rid of our marks. And as a result, our estimate of the population would also be higher because we're thinking that these are chipmunks that we hadn't caught before when in fact we did catch them before. We just lost our measuring tool, which was the mark. So in this situation as well, this would result in our guess to be higher. So our estimate would be higher. Okay, and then another one of these scenarios is that we discover the marked chipmunks are easier to see and therefore more susceptible to predation. So this is saying that marked chipmunks are more likely to die off and like not return in our sample. So this would indicate that we will capture fewer marked chipmunks than we should have, just because they're not in the population anymore, they're dead. So the probability of catching marked chipmunks reduces by a lot. Therefore, the population size that we calculate will also be reduced by a lot. So it's proportionately going down. So it's not that we overestimated or underestimated, just because like as the red chipmunks disappear, our estimate like decreases by the same amount. So our proportions are still the same, but it's just that we're not able to accurately quantify the population. All right, and then finally, what modifications could you make to make the sampling program more accurate? So, what do you guys think would make this experiment more accurate? Thinking about what we've talked about and like what you previously know about accuracy. All right, I can start off with one. So one thing that came to my mind was just, oh, let's see, we have an answer. So use tags that they don't like to lick and also put the tags where the predators can't see them. Yes, that is a great answer. I really like that. So using mark systems that can't be detected by predators. And this would avoid the third scenario that we were talking about in the question. And another thing that we could do is sample more than one parts. Another thing is put up a sampling system that can't easily be licked off of the squirrel or chipmunk. So marking system that can't be easily removed. All right, next we're going to be shifting gears a little bit. So instead of looking at population estimate, we're going to be looking at um, like different levels of density. So like and how they change over time based on mortality rate. So let's see. The following table provides the number of deaths per acre per year resulting from the operation of two different agents of mortality in populations of grasshoppers at different density levels. Fill in the mortality rates of A and B in this table. So basically what we're going to be doing, we're just going to be taking percentages. So for agent A, here we have 4, here we have 100. So we're going to be doing 4 over 100 for agent A. So 4 divided by 100. And then here would be 0 over 100. So this will be 4%, this will be 0%. And if we continue the same logic, this would also be 4%. This would also be 4%. This would also be 4%. But agent B starts increasing more. So we see 2.5% here, 5%, And then let's see, this would be 50% here. So that's how we got the mortality rate, just taking a simple percentages from your population density. So just make sure that this part is population density and that this part is death per year. So if you have those two things, then you can calculate your mortality rate. And then let's see, a graphical representation of it could look something like this. So we saw that agent A stayed the same at 4%. So agent A stayed the same at 4%, whereas agent B increased. So that's what we see here. So agent A just, these are really thick lines. Let's see. Okay, so agent A we see stays in a straight line. And then agent B, we start off at 0, goes up, and then just drastically goes up. And we also saw those in our numbers. So we see it started with 0, went up a little bit, went up by a half, and then from 5 it shot up all the way to 50%. And that's what we see in the graph here. And then for our few questions. Okay, so which two of the agents of mortality, A or B, is operating in a density independent manner? So what do you guys think? Do you think A is acting in an independent manner or B is acting in an independent manner? And here's the graph again, this might help. Common says A, and that is right, because here we see no matter what happens to the population density, whether it's 100 or 100,000, it just stays at 4%, which means it doesn't really care about how big the population density is. So so we say that it's acting in an independent manner, whereas B, we see that it depends on the density. So at 100 it's 0, but then at 100,000 it's at 50%. So it does care about how dense a population is and how it affects a population that's more dense. Okay, and then which one do you guys think acts as a factor stabilizing the size of grasshopper population? So which mortality agent do you think tends to stabilize a population? Here's the graph again in case that's helpful. I'm seeing agent A, but it would actually be agent B. I can see why you think it's A because A is like constant over time. We might think that it tends to stabilize the population, but it's actually B because say you want a population to stay at 50 individuals, like you don't want it to go more, you don't want it to go less. If agent A was acting, then agent A is only going to remove 4 people every time. So even if the population's at 50 or if it's at 150, agent A is only going to remove 4% of that, which means that as your population increases, it's not being stabilized, it's still increasing because Agent A is removing the same amount as it would even if the population was 5. But then for factor B, it's proportionally taking away people. So at a lower number, it's taking away lower people. At a higher number, it's taking away higher people, which means it's helping the population be stable around a similar value. Yeah, I hope that makes sense. If it didn't, let me know. Yeah, another way you could think about it is like no matter how large the population is, A is only going to remove 4%, which means as the population gets big, it's not going to stabilize because it's going to let the population get big. Okay, let's see. Comment says so B has the most drastic effect on the population, so it has more influence on stabilization. Yeah, and I would also think about it in terms of like proportion. So it does have the drastic effect on population, but on the other hand, you also see that as a population increases, the amount that B kills the individual also increases. And then it goes the other way. Like if a population is smaller, then B kills smaller people. So it has a linear proportion to it, whereas A is just stable. It just doesn't care whether it's big or small. Whereas B kind of adjusts to whether it's big or small. All right, that was our last question for today's worksheet. Any other questions that you guys have? All right, I'm gonna put the extra credit link in the chat and make sure to fill it out. Thank you, and yeah, you too have a great weekend. All right, everyone, I hope you've gotten a chance to open the link. I'm gonna end the live stream right now. Thank you for coming and being interactive through the chat, and I'll see you guys next week. Bye.